Okay, so hey, I'm Michael. I will be co-presenting alongside Hernan and Gal. Our Y data mentor is Etam, and our K health mentor is Tom. And today we're going to talk about the project. We're going to do a project and company introduction. Then we're going to discuss the pipeline that we went through. And then we're going to discuss about how do we get from results into insights. So let's get to it. Start with the company. So K-Health. K-Health is a medical AI startup working with association with Maccabi Health Care Systems. The main product of K-Health is K, which is an AI personalized health assistant. Basically, you tell the app what's going on with you, and it tells you what are you sick. Our mentors, Tom and Etam. Hi. And now let's talk about the project. So the project is called From Concept Discovery to Differential Diagnosis. And what is the business problem? So basically, each doctor visit log has closed fields and free text fields. The application currently does not make full use of the free text fields. And actually, the current medical ontology was mostly manually built by domain experts in the medical field. And our main objective is to build an automated ontology learning from medical visits. So let's talk about ontology learning and about ontology before we talk about ontology learning. So what is ontology? So the formal definition is a set of concepts and categories in a subject or a domain, our case, the medical domain, that shows their properties. So in this illustration, you can see that we have disease, we have patients, we have symptoms, drugs and medications, and also the relation between them. In our specific project, we focus on finding the concepts. The data, let's talk about the data. So we were working with pediatrician data for Maccabi, meaning ages 3 to 18. We work with over 6.5 million entries that contains 78 unique medical conditions like chickenpox, viral infections, influenza, sinusitis, and more. And the free text features that we worked on are the patient complaint and the doctor findings. But now let's translate this into the machine learning world. So what we wanted to do is first, we want to extract the entities out of the data. For example, dates, family members, locations, drugs, symptoms, and more, of course. Out of them, we want to detect the important concepts that are relevant for our ontology, the medical ontology. And the last part is we want to facilitate a way to detect and visualize relations between different medical concepts. So the pipeline goes as follows. We did exploratory data analysis. Afterwards, data pre-processing. We built a baseline model. Afterwards, we did token embeddings and hierarchical clustering. And I will let Hernan lead and explain about it. Hernan?
Thanks, Michael. So as Michael explained to everybody, we want to try and define concept, as complicated as it might sound. So let's go ahead and see what we did. Next slide, please. We started with an EDA, with an exploratory data analysis. We wanted to drill down on a certain condition, and we chose chickenpox because Michael confided with me that he never had it and he was curious. So we checked some information about the chickenpox, for example, the age of the patients that got the diagnosis. We can see it on the left-hand side. We thought it was interesting that it behaves exactly as you would expect as exponential distribution because you can only get it once, right? So the probability of you getting it goes down as your age goes up. And on the right-hand side, we see something that it's more NLP related. We see the average number of words that the doctor needed to use in the finding field to describe different conditions. Highlighted is the chickenpox somewhere in the middle. And we can see that you can distinguish between different conditions just by counting the number of words. Can we go to the next slide, please? And we also printed the TF-IDF values to see what are the most important tokens to describe this certain condition. We can see the trash is right there at the top, and it makes a lot of sense, right? So then we went into the NLP field. Next slide, please. And before we get into all the things we've done, we came across some challenges that are unique, that are due to the fact that any NLP task is hard, but NLP tasks in Hebrew are currently extremely hard for a few reasons. First of all, there is a lack of existing packages that help facilitate the entire process. There's very hard word ambiguity. Many words that are, have different meanings are written exactly the same. It's a challenge to tokenize those words and to separate words from the reference letters that accompany them. And moreover than that, that's just for NLP in Hebrew. Medical NLP in Hebrew, it's even more distinguished of a language, more specific of a language, and that makes the task even more unique. Next slide, please. So after some pre-processing, that we got the entries as data, we worked with the lists of sentences and list of the tokens in the sentences. You can see that we can't show naturally all the data because medical data, it's a bit sensitive. Next slide, please. So after we had our data, we wanted to see whether at all it was possible for a machine to learn medicine just by reading the text of doctors. So we did a baseline, very simple logistic regression model in which we fed it the data, the raw data, the words, the tokens within the data, and predicted the condition. We can see that we got about 57% accuracy. It went up to 83% accuracy when we tried to predict 1 out of 3 conditions. And that encourages us because we saw that without doing too much, there's a lot of meaningful information that can be drawn out from the text. And our mission now is just to try to understand how to define the different concepts. Next slide, please. So then we tried different numerical representation systems because we wanted to calculate distances and everything. So we tried co-occurrence-based methods, meaning that we counted how many times each of our tokens in our vocabulary, that by this point, after we added bigrams and trigrams, consisted of almost 20,000 tokens, distinct unique tokens. And we also tried to train GenSim's word-to-vec embeddings. Next slide, please. And one of the greatest challenges that we had all over this project was to come up with methods to evaluate it, because of course it's an unsupervised challenge. So we decided that we'll go with the embedding system, with the numerical representation system that clusters the most similar words together, that the distances between words and different pronunciations or maybe typos or stuff like that of the words are the words that are closest to a target word. And we can see that across the board, all of the systems that we tried had some success. For example, in trying to find what are the most similar words to the word Gerut each. Next slide, please. But word-to-vec was the only method that we tried that has consistent success. We can see that we get good results when we're trying to find the most similar words to the word fever, and in the other method, it's just all over the place. So we went with word-to-vec embeddings. Next slide, please. And then when we had our embeddings, we decided to do hierarchical clustering. The reason that we decided to do hierarchical clustering is because it allows us to do 2 things. First of all, to cluster vectors of words together and to explore the relation within each cluster, and also to look like in other levels and to look at the relations between those different clusters that we thought will represent entities, units of semantic meaning. Next, please. So we performed hierarchical clustering in a few methods. We wound up choosing word, and we came across some new problems, that the clusters that we had were very different from one from another, both in the sizes, the number of tokens that got mapped into each individual cluster, and both in the amount of work that each cluster had to go through. Some of them were very concise, very cohesive concepts, and some of them we had to break them down furthermore, and Michael will expand on that in a little bit. Next slide. But we did see some interesting patterns right off the bat. for example, we can see on the left-hand side that we have like a cluster that it's very, very further apart from the rest of the clusters. And when we started investigating, we saw that those are all the English common words, because most of our data was in Hebrew, but some doctors write their documents, their encounters in English. So all the words in English that aren't specific terms from the medical field were clustered together on the side, like noise clusters. And we also saw that we have a lot of redundancies, a lot of words that are very similar to one another, a lot of tokens got mapped to very, very far apart from each other. In the box in the left and box in the right, we had very similar words. And when we started exploring that, we found out that it might be that the linguistic way that the doctors write in the complaint field and in the finding field are a bit different from one another, and it causes the fact that similar words got mapped very far away one from another. So we decided to split the data up at this point and to explore the findings field separately and the complaints field separately. So now we have the clusters, and Michael will talk about how we define medical entities out of them.
Thank you, Hernan. So let's talk about the issues and challenges so far. So up to this point, Hernan mentioned the pipeline that we went through, and now we have entities. And I'm going to go over them one by one. So let's start with the first one, entity scoring and validation. So we want to identify which entity is good and which entity is bad. So the score we came up with goes as the following. We take the minimal distance between clusters, we divide it by the mean square distance within the cluster, and we multiply it by the log of the number of tokens in the entity, just because we want to give a small edge to good clusters with many tokens. And now we have the score, and we can go off to the next task, which is an automated way to drill down into clusters when we need to, and an automatic way to cut off the dendrogram. So we came up with a recursive algorithm that actually checked the score that we came up with, and if the score is larger than the threshold, we stop. We say, but if it's not, we search for more split, we optimize the cutoff value, and we stop when we hit the stopping criteria. Now we have a different challenge because we want the entity naming to make sense. However, we are still in an unsupervised world. So we came up with two ways. One is frequency-based. So we just take the most common token. And the other one is embedding-based, where we take the token that is closest to the mean of the embeddings. Another challenge solved or tackled. Now we have a different challenge, identifying relationships between entities and conditions. So we chose to use affinity for this purpose. So we take the conditional probability and divide it by the overall probability. So let's take a look at two examples. Let's say we have an entity that is representative is Girud, and let's see what conditions got the higher affinity. So enterobiosis, dermatitis, allergic reaction, hives, chickenpox, makes sense. And if we do it in a reversed manner, we take the chickenpox and we examine the entities, we see that ababuot, pricha, wounds in the face just pop out, which is quite awesome, to be honest. But we can even take it one step further, and we can plot the affinity and frequency together. So as you can see here, the chickenpox on the top right actually got both the highest score and both the highest frequency for the entity pricha. Makes sense. And now I will give the lead to Gal.
Thanks, Michael. Up to you, Hernan and Michael have presented all of the artwork that we did so far. But then we found ourselves in another situation. Can you please go to the next slide? Thank you. We wanted to do more. And we wanted to do a couple of things. We wanted to know what are the connections between those entities. How those entities represent different conditions. After all, we have 78 conditions in the data. We wanted to know if we can distinguish between real medical entities to some noise, like Hernan said earlier about those two clusters. And we wanted to drill down into the entity view to understand what's inside each entity, how it's being distributed, what words does it represent. Can you please go to the next slide? Thank you. But in order to do this, there are a couple of challenges that we must overcome. The first one is that working with the raw results, it really wasn't that easy. Another thing is that the hierarchical clustering doesn't give out those insights that I described that easily. And we couldn't visualize the relations between the condition and the entities. And the last one is that gaining insights requires a high technical understanding. So we try to think how can we give the experience to do all of the things that I've described. And we came up with developing our application to explore the data. And I'm gonna show you a couple of the features that we worked on in this application. Can you please go to the next slide? Thanks. So the first one is that to have the feature of interactive tree exploration. This feature actually gives you the ability to explore the tree by yourself. You can go down the branches, go between branches, see, and like play with the tree. Can you please go to the next feature, Michael? Thanks. The second one is the quick pick feature, which allows you to over one of those entities and see the statistics inside of it. For example, you can see there the main cluster name, the secondary cluster name. You can also go and check the plot that Michael described about the affinity. You can also see the cluster score and the condition and the affinity condition score for each of those 10 conditions. Also, you can quickly see like the words that are inside the entity, which is down there in the window. Can you please go to the next feature? Thanks. Another feature that we thought that would be really useful is a feature that will help us to find the meaningful paths for us. For example, first of all, we added a controller down in the window that you can click on, and it will guide you to the entities that holds the representation for the condition that you want to discover. So in this example, for example, we are checking the chicken pox, and the entities that hold the information about it is being highlighted in green. The more that you are green, the greener you are, the better you are for this condition. Can you please go to the next slide? And the last one is one of my favorite, actually. After we've done all of this exploration, you are allowed to have some kind of ontology detection. What I mean is, here, for example, we see the viral infection. After we've opened all of those branches, we can see the entities that represent this condition. For example, we can see that vomiting, throwing up, diarrhea, sore throat, headaches, coughs are a part of this condition that is a viral infection. Now, can you please go to the next slide? Thank you. So this is an acute sinusitis example. I actually never heard about acute sinusitis before, but I do know now that when I'm looking at it, I can see that it's similar but different from viral infection. Different entities being led up. For example, I don't see here in here, diarrhea doesn't exist, for example. Or for example, I consider it's in the forehead. So it's really helpful to have some ontology detection to understand and deduce about the condition. Now, I actually wanted to do a live demo, but because of information security, I'm not allowed. So what we did, we made a little video of me playing in the application, so you could see it. So in here, I'm playing with the condition, chickenpox, viral infection, and I'm starting to explore and play with the tree. On the left side, you can see that whenever I'm moving over some kind of condition, it changes, and I will do it soon. It changes, and you can see more about it. And now again, I can just play and see which related to which. And I had a bit of list. You can check the graph that Michael talked about. Michael will take it for me.
Michael, you are on mute.
We can hear.
Sorry. So for now, we have two questions. Where can we do better? And where can we take it from here? So about the data pre-processing, we can do better tokenization and separation between words and relational letters. We can also have better pre-processing for the English tokens. We focused on the Hebrew ones. About embedding, so we can do even more hyperparameter tuning. We can use different models. We can use ensemble. And about the cluster automation, we can improve the formula to represent better how well the cluster is. And actually, we presented it to K-Health, and they were very excited, and we discussed where can we take it from here. So we can actually use, instead of the bag of tokens that Hernan used, we can try to use the bag of entities and see whether a classifier will be better. It's very interesting to know. And about the from results to insights part, the application, we can even make more parameters adjustable, like the change, like the threshold. And then another interesting idea that came up is that we can integrate the domain expert feedback into the automation process, and thus enhancing our model. Yeah. So thank you very much for listening. We really appreciate it.
Thank you very much. So, yeah, the time for questions. I'll ask the first question. When you are talking about to do it better, so how do you evaluate what is better here? What does it mean better?
Hernan, I saw you're unmuted, so you take it.
That's a great question. And better is, and again, finding out methods to evaluate ourselves was a challenge for us throughout all the project. And a lot of the time, we just decided on what us laymen thought about the conditions that we have, the cluster that we have, the entities that we have. But as Michael talked in the previous slide, we want to integrate the domain knowledge, the domain experts, the domain experts, their knowledge and their feedback, so they can tell us what is a good entity and what is better, and whether it needs to be more broken apart or more general.
And did you spot or experts spot some weaknesses in your models, and what are the areas, or what are the conditions, or whatever where you should do better?
So not yet, because generally they haven't got, like, everything that we showed so far was just the project that we have. And the optimization values that we have are optimization values that we chose on what we thought would be good. So that information, that feedback from experts is something that it's not yet integrated, but it will surely improve the project.
Just to add to this part, so actually one of the algorithm researchers said that we need to talk. He said it yesterday because we presented yesterday. So hopefully we will get some feedback from them as well. We naturally saw places where entities are good and entities are bad. It happens. It just happens. Some of them are not good.
Mm-hmm. Okay, other questions?
Yes, I would like to ask a question. I think at the beginning of the presentation, you were talking about the business problem definition, and you were talking about an ontology. And maybe I missed it, but I can't find going back to this ontology. Did you manage to, what I did see was embeddings, but there is still a step from there to getting an ontology which actually connects the entities with some sort of a type of connection between them. So did you tackle this or try to go there?
Yeah, it's a great question, and yeah, let's talk about it. So our tool is not supposed to replace ontology creation by domain experts in the medical field. It cannot, it won't be done in K-Health for sure. What happens before is that the medical expert went through the raw logs They didn't have any tool to assist them. So we are talking about hybrid between man and machine working together to create and explore ontologies. You can take this method to Spanish the doctor logs about the elderly people, and then easily try to extract the basic ontologies and investigate whether your intuition are correct. It will not replace the domain experts. It will be a tool for them.
Yeah. It's a tool for domain experts, for them to say, because after all, we are not the domain experts, and we can't tell them what ontology is good or not.
Okay, thank you.
You have time for just one more question?
I have a question regarding, probably I also missed it. How did you actually, because the thing is that I've been working on some similar project in my previous company. We also have been trying to build an ontology for other domain, but it's not medical, but it was also quite hard. It was marketing. So my question is, how did you manage actually to separate conditions and entities in the first place? When you're doing hierarchical clustering with embeddings, what you get is that still some clusters will include also conditions and also entities. So how did you separate them? How do you understand that if they're located in the same cluster, that they're connected in this kind of connection?
It's a great question as well. So actually, the conditions are a separated field. So it's not it's not the field we find in the data. It's like, imagine another column with a condition ID. Yeah, yeah.
So it was separate. It was a supervised way to separate them.
Yeah, imagine the doctor like picking the condition in the menu, you know?
Okay, that's great. That's a good luck. Because that's really a hard thing to do usually in ontology building.